Before we get started on section 2.2, I'm going to give a brief overview of limits and the concept behind what is a limit. Let's look at the following graph. As x approaches 4, what does the y value approach? If we're approaching 4 from the left, or let's take from the right side of 4 first. Let's take 6, for instance. Let's look at the corresponding y value. We'd have that as our corresponding y value. Let's move closer to 4. So let's let x equal 5. Well, the y value would be here. Let's choose an x value approaching 4 from the left, so maybe 4.5, and the corresponding y value. So you see, as the x values are approaching 4 from the right side of 4, what's happening with the y values? We can see the y values are approaching 2. Now we could do the same analysis from the left side of 4. We could say as x approaches 4 from the left side of 4, let's take a look at what's happening with the y values. The y values would also be approaching 2 from the left side of 4. So we can answer the question as x approaches 4, y approaches 2. This could also be written as, here's another graph. X approaches 4. Let's do the same analysis. As y approaches 2. X approaches 1 as y approaches what? As the values of x approach 1 from the right side of 1, let's take a look at those y values. Those y values are coming down and approaching this value here. Let's do the same analysis from the left side of 1. As x approaches 1 from the left, the y values are approaching this value here, which would be 0. So we could state that as x approaches 1, as y approaches 0. That's the idea behind a limit of a function. Here's another graph. We have a trig function here. X approaches pi by 2. Here is pi over 2, 0.5 pi. As y approaches what? Well, let's do the same analysis. Let's let the x values approach pi by 2 from the left and look at those y values. Okay, there are the y values approaching. Looks like it's approaching 1 from the right side. As x approaches pi by 2 from the left, let's look at the y values. The y values would be approaching 1 also. So we could state x approaches pi by 2 as y approaches 1. Okay, here's another graph. Notice this graph, at x equals 2, it appears that the function is undefined. There's an open circle. But we're going to do the exact same analysis anyways. Let's approach 2 from the right side of 2. We're approaching 2. Let's look at what the y values are approaching. The y values are approaching 4. Let's do the same analysis from the left side of 2. The values of x are approaching 2 from the left. Let's look at those y values. Those y values appear to be approaching 4 also. So we don't have to be defined at the value of x that we're looking at. When we're working with limits, the important word I'm saying is approaching. As x approaches 2, what are the y values approaching? Now, all of these examples, the last 4 examples, can be written in limit notation. Let's take a look at how those graphs would be written, or the limits would be written in limit notation. This was the first graph we looked at. The graph actually is the square root of x. We were looking at x approaches 4 as y approaches 2. So written as a limit, we would have the limit of the square root of x as x approaches 4 equals 2. Second graph, we had the graph y equals x cubed minus x. We were looking at x approaches 1 as y approaches 0. Written in limit notation, we would have the limit of x cubed minus x as x approaches 1 equals 0. I've taken the limit of that entire quantity. The next graph we looked at was the trig function. That is the sine of x. We looked at as x approaches pi by 2, y approached 1. So written as a limit, we would say the limit of the sine of x as x approaches pi by 2 equals 1. And the last graph, as x approaches 2, y approaches 4, written as a limit, we would have the limit of this function. This would be a piecewise function, but we saw this piecewise function was not defined at x equals 2, but that doesn't matter with a limit. The function does not have to be defined at the particular x value. It's what are we approaching? Is the y value approaching 4 from both the left and the right side? Yes. So the limit of f of x as x approaches 2 equals 4. Here's another graph. We have x all over x minus 1. Let's look at finding these limits. The limit of x over x minus 1 as x approaches negative 0.5. So let's go through the same analysis we did on the other graphs. Here is negative 1. So this would be negative 0.5. So as we approach negative 0.5 from the right, what's happening with the y values? It's approaching this value right here. And as we're approaching negative 0.5 from the left, the y values are approaching that same value. Now we're going to approximate this value. Here this would be 1. So it appears this would be 0.5, so a little less than 0.5. So we may say 0.4. The limit of x over x minus 1 as x approaches 0. So as x approaches 0 from the right, let's look at the corresponding y values. And those appear to be approaching 0. If we approach 0, x equals 0 from the left, we're looking at the y values. What are they doing? They're approaching 0 also. So we would say the limit of x over x minus 1 as x approaches 0 is 0. The limit of x over x minus 1 as x approaches 2. So let's approach 2 from the right side of 2 and look at what's happening with the y values. Here our y values approaching here. And from the left side of 2, as our x values approach 2 from the left of 2, what's happening with the y values? They're coming down here like this. So it appears that our y value is approaching 2. And the last one, the limit of x over x minus 1 as x approaches infinity. Now think through this one. We're not approaching some value. We're letting x get larger and larger and larger and larger. And with limits, we're looking as x gets larger and larger and larger, what's happening with the y values? There appears to be, here's another graph. Horizontal x approaches -2 from the right here as y approaches. So if we were able to see more of the graph, it appears now this is called a one-sided limit because we're only concerned with as x approaches -2 so we'd say the limit of x over x minus 1 as x approaches infinity. What's happening we're looking at y values. What is the y value? So let's build a table of values. Is the y value approaching something? Yes, 1. If we were to complete this table of values, this function that we're working with is y equals x squared. So we would plug these values into the function. So we would have negative 0.5 squared we have negative 1 squared, negative 1.5 squared, negative 1.9 squared, and negative 1.99 squared. So we're looking at this numerically. So if we wanted to analyze what the y value is approaching, well, as x gets closer and closer to -2 from the right, the y values seem to be approaching, looks like 4. That would be my guess at this moment. And if we looked up at the graph, as x approaches -2 from the right, so let's let x approach -2 from the right, we're looking at what are the y values approaching? And it does appear that it is approaching 4. Now let's look at x approaches -2 from the left. See what the y value approaches. And again, we're going to look at this numerically first, and then we'll look at it graphically to see if we can verify our results. So if we plugged in -2.5 to our function, -2.5 squared, 6.25, -2.3 squared, 5.29, -2.2 squared, 4.84, -2.1 squared is 4.41, -2.01 squared, 4.04. It appears that the y values are approaching 4. And if we looked at it graphically, x approaches -2 from the left. Let's look at what happens with the y values. So it does appear that we are approaching 4. How can we represent a one-sided limit? To write a one-sided limit to represent x approaches -2 from the right as y approaches 4, and x approaches -2 from the left as y approaches 4 would be written like this. Notice the difference is that right here, that means we are approaching -2 from the right side of -2. So that makes it a one-sided limit. And through our analysis, we saw the one-sided limit, the limit of x squared as x approaches -2 from the right equals 4. The other one-sided limit, notice here we have this little negative sign up here. That means we're approaching -2 from the left. So this would be read as the limit of x squared as x approaches -2
When we are working with limits,
in
4.
order for a limit to exist, the one-sided limits must equal each other. That's how we determine if a limit exists. We look at the one-sided limits and see if they equal each other. If they do, then that limit does exist. So in our last example, we saw the limit of x squared as x approaches -2 from the right. That equaled the limit of x squared as x approaches -2 from the left, and we found that result to be 4. So we can conclude that the limit of x squared as x approaches -2 equals 4. We've shown that that limit exists by showing that these two one-sided limits equal each other. Let's try another one. Here we have the limit of the natural log of x as x approaches 1 from the right. As x approaches 1 from the right, let's look at what's happening with the y values. So the y values from the right are coming down to this point. So that appears to be 0. Let's look at the other one-sided limit, the limit of ln of x as x approaches 1 from the left. So our values of x are approaching 1 from the left. So we're going to analyze the corresponding y values. Those y values are approaching 0. What can we conclude from this? We can conclude that the limit of ln of x as x approaches 1 equals 0. Because the one-sided limits equal each other, this one-sided limit equals this one-sided limit. Therefore, we know the limit of ln of x as x approaches 1
Here's another function
equals 0.
This is
called the greatest integer function. Look at the limit of this function as x approaches 3 from the right. The greatest integer function is defined as, if we plug in a value for x, we want the greatest integer less than or equal to that number. The greatest integer value would be defined here, not defined here. Defined here, not defined here, and so on. Let's go back to our limit. The limit of f of x as x approaches 3 from the right. So let's let our x values approach 3 from the right. We're going to analyze what's happening with the y values. That appears to be approaching 3. Remember, the function does not have to be defined at that particular point. It's what are we approaching. What about the limit of f of x as x approaches 3 from the left? So let's approach 3 from the left and analyze the corresponding y values. So here the y values are approaching this value here, which is 2. So what would we say about the limit of f of x as x approaches 3. Since our one-sided limits, this one-sided limit does not equal this one-sided limit, these are not equal. Therefore, this limit does not exist. DNE does not exist.
Now, what about a limit that looks like this? We have the limit of
in
d
order
squared
for a limit to exist, the one-sided limits must equal t2 minus d. And we're looking as d approaches 1. Now, if you think back to those limits we were looking at earlier, we were able to directly substitute the value into the function if it was defined at that point. So the idea behind this problem would be, if I have the limit of d squared minus y over 2 minus d as d approaches 1, I could directly substitute 1 in for the value of d. So I would have this. That would be the value of this limit. Now, we're going to look at the limit of a function graphically and numerically. Let's look at the behavior of the function x squared minus x plus 2 for values of x very close to 2 but not equal to 2. We're going to look at this numerically first. So if you graphed this and looked at these in your table of values on your graphing calculator, take a look at what's happening as x approaches 2 here, 1, 1.5, 1.8, 1.9, we're getting closer and closer and closer to 2. So we're looking at the corresponding y values. What happens as x gets closer to 2? It appears the y values are getting closer to 4 down here. And likewise, if we look from the right side of 2, 3, 2.5, 2.2, 2.1, and so on, what's happening with the corresponding y values? Well, they're approaching 4 also. And in the last couple of slides, we said in order for a limit to exist, we have to be approaching the same value from each side of that value we're looking for. So we could conclude that the limit of this function as x approaches 2 is 4. Look at the graph of that function we just analyzed. Graphically, if we analyze this, as we approach 2 from the right, let's look at the y values. It appears that's approaching 4. And the x values approaching 2 from the left. Let's look at the y values, what they are approaching. That's approaching 4. So again, we could conclude that the limit of x squared minus x plus 2 as x approaches 2 equals 4. Because our one-sided limits equal each other, this limit exists. The notation for a limit, we said, is the limit of x squared minus x plus 2 as x approaches 2 equals 4. Now the definition of a limit, the limit of f of x as x approaches a equals L, some number, is said the limit of f of x as x approaches a equals L. That indicates that limit exists. This means we can make f of x arbitrarily close to L by taking x to be sufficiently close to a, but not equal to a. Example, guess the value of this limit. If we looked at it graphically, what would your guess be? Let's do the analysis. Let's approach -1 from the right side. Well, the y values are going off to infinity, it looks like. As we approach -1 from the left, the y values appear to be going off to -infinity. So we would conclude that this limit does not exist. Another example. The limit of the square root of t squared plus 9 minus 3 all over t squared. Now here's the graph of that function. We really can't tell what's going on as t approaches 0. It looks like if we just had to guess, I'd say probably 0. But let's zoom in around 0 to see if we can determine what's going on with the graph. So let's zoom in. Zooming in didn't really help, did it? That doesn't clear it up. Well, let's zoom in one more time and see if we can determine anything from zooming in one more time. Again, it appears that as x approaches 0 from the right side, we're approaching 0, and as x approaches 0 from the left, we're approaching 0. However, if we looked at this numerically, we would see that this is not approaching 0. It's actually approaching, I believe, 1/6. So that's the problem with looking at limits graphically. Sometimes we can't really tell exactly, or we get a false reading from a graph of what the limit actually is. So that's why we're going to move from looking at limits graphically and numerically to analytically. Another example. In the next section. Find the limit of sine of x over x as x approaches 0. Let's do that graphically. Now, one thing that we probably would notice is that this function is not defined at 0. If we plugged in 0, the sine of 0 is 0 divided by 0. So it's not defined, but that does not matter. We said if x is approaching 0 from the right, y is approaching 1. If x is approaching 0 from the left, we see the y values are approaching 1. Therefore, this limit does equal 1. It does not matter that that function is not defined at 0. It's what are we approaching? What are the y values approaching? Let's look at this limit graphically. Here, we can't really tell what's going on, so let's see if we can zoom in a little and determine what's going on with that limit. And again, this doesn't help whatsoever. But if we analyze this function a little bit, we would see that the sine of pi over x as x approaches 0 would just be oscillating. Infinitely, it's oscillating as we get closer to 0 from the right side, and it's infinitely oscillating as x approaches 0 from the left side. So this limit, we would indicate that this limit does not exist. The y values are not approaching the same number from both sides. So this limit does not exist. The limit of x cubed plus cosine of 5x over 1,000. If we looked at this graphically, we would probably think that limit is 0 because we're approaching 0 as x approaches 0 from the right. It looks like the y values are approaching 0. And as we let our x values approach 0 from the left, I did that backwards, but we see it's approaching, it appears that it's approaching 0 values.
However, that is not
See
the
if we
case.
can determine anything different.
Let's take a look at the table.
There's our table of values. So we probably would conclude from this table of values that as we get closer and closer and closer to 0, our x values are getting closer to 0, it looks like we're getting 1 over 10,000. So that's what our limit would equal. 1 over 10,000. The last example is called the Heaviside function. Let's graph this one. We're trying to find the limit of h of t as t approaches 0. Now here's the graph. You can't see it very well, but it's along this line here. Now it is defined here and not down here. All right, so as t approaches 0 from the right, what's happening with the y values? Now it appears the y values are approaching as t approaches 0 from the right, we're approaching 1. But the limit of this function as t approaches 0 from the left, here it appears that the y values approaching 0. So our conclusion would be this limit does not exist.